very much. And I've realized I need to go and get a little cable out of my bag. So I'll be back in about 30 seconds.
You want this one? Is that good?
No, that's not the right one. There we go. Okay, I like to keep you waiting. So I'm going to take the other end and plug that into there. And hey presto, we're on the wrong page. All right, let's start at the beginning. Okay. Does this microphone work? Yes. Does this microphone work? Oh, there we go. Okay. So at least I can not be completely stranded behind the lectern. Okay, hello everyone. Thank you for all being here, and thank you to the organizer of this event, especially Dr. Fred, who's done a very fantastic job in putting all of this together, and our other speakers who've been fantastic, and it's been a very enjoyable evening so far. So I hope you're all feeling relaxed and refreshed, and not yet tired and emotional. So I'm here as a mathematician, so I guess maybe things are slightly harder for me, because I don't study very small things. I don't even study very large things. I just study things that don't exist at all. And so somehow I have to work out how to tell you some stuff about mathematics in a way that I can kind of live with myself about. And I decided the only way I could do this is if I actually taught you a bit of maths. So in my notes, I've got a little note that says, pause for stampede to bar. But that seems that hasn't happened, so I'm very pleased about that. And so, okay, so what I'm actually going to do is I'm going to sort of come at the maths quite slowly. I'm going to start by asking a really important question, which is not that related to maths. So why do computers consistently do the opposite of what you want them to do? So I'd like to ask a question. If you'd like to put your hands up if you've sworn at your computer in the last week. So I actually haven't sworn at my computer. And the reason is that my wife taught me this amazing trick, which is that if your computer annoys you, you should hiss at it. It's amazingly satisfying. You just stand there and you go, sss. And so I've been doing that quite a lot the last week. And so all of us have this issue. And we might ask, why is this? What's going wrong? Whose fault is this? So there are three possibilities, right? It could be that it's your fault. It could be that it's the computer's fault. Or it could be that it's someone else's fault. You can tell I'm a mathematician because I've enumerated all possible cases now. Okay, so if we were, say, 100 years ago, then you could say with almost certainty that what went wrong was to do with the computer. Okay? So there you can see some vacuum tubes. So they're either very fancy light bulbs or very primitive transistors, depending on your perspective. And so they were what the first generation of computers ran on, and a typical computer would have like 6,000 of these valves in it, and they'd kind of blow once every few hours, if you're lucky, maybe once every half hour or something like that. And so you just started doing a calculation, then it would kind of all blow up, and you'd have to go and search through all the valves and find the one that had blown and replace it. Okay, so computers are a lot more reliable today, and so I guess we're pretty fairly certain that probably there isn't a transistor that's blown up inside our computer if it stops working. I mean, it does happen. You can zap it with an electrostatic shock and blow it up. That is possible. Or it can get struck by lightning. Or perhaps it could be a different kind of fault, like the San Andreas fault. So it's quite remarkable if you think about it. Wouldn't it be a really bad idea if you took the foremost concentration of computing knowledge and expertise and placed it on top of a highly geologically unstable area? And so I think a lot of people are just waiting for the crunch event, after which we'll suddenly be no longer be able to buy anything online ever again, because it'll all gone down a big hole in the middle of San Francisco. Okay, and so the other option is that it's not the San Andreas fault, it's actually your fault. And maybe I'm being a bit harsh on there, right? Okay, it might not be actually your fault, it might be someone's fault. Okay, and so this is normally what is the case. It's not the computer's fault, it's someone's fault. Now, quite often, it's not actually your fault. It's the fault of whoever put together what's running on the computer. Okay, and so there are various aspects in which what's running on the computer can go wrong. So let's maybe try and work out what those aspects are. So to motivate this, I'm going to show you some advice that I found when I was furiously searching on the internet how to give a public talk. And it said I should explain what I'm going to say, and then say it, and then explain what I just said. Okay, I think this is bad advice because it's basically telling me to treat my audience like they don't really know what they're doing, okay? And I think you all know what you're doing. See, I also learned that you should compliment your audience when you're giving a talk. So this is bad advice, I think, for a public talk, but I think it's quite good advice for writing a computer program. So this is how you should write a computer program. First of all, you should describe what it's going to do. Then you should write it, and then you should check that it does what it said. And so all these three aspects have names, right? So this would be called specification. This would be called implementation. And then this would be called verification. Okay, sounds simple, right? But the thing is, in all of those stages, there are various ways in which this can go wrong. Okay? So let's have a look. So this is how not to write a computer program. So step one is to describe what it's going to do, but do it really badly. Okay? So you're going to tell people you're going to either do it in a sloppy way that doesn't specify completely its behavior, or you're going to do it in a way that's simply not what you actually want. Okay? And so you would call this, I suppose, a specification error. So the next thing you could do is, you're a bad computer programmer, you take your specification and you just type a load of rubbish that the computer doesn't even understand. Okay? So your computer has a language, and that language you have to type following certain rules, and maybe you don't follow those rules. And so if you do that wrong, you'll invoke a syntax error. The computer will complain loudly, and your program will collapse in a heap of smoke. Okay, now you may get past that point. Okay, so your specification is correct. Your program has correctly typed in code, and the computer accepts the code. However, it may be that the code does not do what it was supposed to do. Okay, so maybe your specifier told you that they wanted you to add two numbers together, and so you wrote a program which took those two numbers and they multiplied them together. And so you give that back to the specifier and say, I wrote your program for you. And he looks at it and goes, great. And if he doesn't check what you've given to him, then he's going to go away and be terribly disappointed when he tries to add two numbers together and submit it for his exam. Okay? And so this is a logic error. So it's a program which looks okay, but in fact does not do what it's supposed to do. Okay, so the problem is now, how do we avoid logic errors in a computer program? And there are various levels at which you can do this. And so here we go. So level one is you take it and you test it under normal use conditions. Okay? So you've got something that's supposed to be a word processor, and you go and you process some words in it, and it seems to do what it's supposed to do, and okay, great, thumbs up. So this is what you're supposed to do, which is to test it under abnormal use conditions. Okay? So imagine you've got something that's like controlling an aeroplane or something. Most of the time, the autopilot just sits there and it kind of lands your plane for you and everything's okay. But then, of course, the situation is what happens if a bird flies into your engine or something like that. Then you want to make sure that the automated control system responds appropriately to that situation as well, right? So you should test not only under normal conditions, but under all conditions you can think of. Now, the thing is, you may not think of everything, okay? So there's always some even more twisted way in which things can go wrong than you can imagine. And so the ultimate, if you like, is to prove that your program is correct using mathematics, okay? And so that's what I'm going to tell you a little bit about. This is terribly embarrassing. What time did I start? 12 minutes. Okay, great. Perfect. Okay, so I'm going to tell you about the practice. I'm going to tell you about the theory. And we're going to concentrate on the theory because that's where I'm at, I guess, about the theory. So the practice is, so this is a project which I just wanted to promote a little bit. So this is an Australian project. It's called SEL4, okay? And so what this is it's a verified microkernel. So what does that mean? So a microkernel is a thing that controls the very basic level of a computer system, right? So just the absolute basic level that interfaces directly with the hardware and kind of, right. So if you think of your operating system, it's way below that. Like it's right down, sort of just above the chip level, basically. And so to say that it's verified means that they've written a complete specification for what it's supposed to do, which is kind of a completely rigorous thing. And then they've used a computer program called a verification program to check mathematically that everything that their code is supposed to do is actually done by their code. Okay? And so there's absolutely no way in which the program can deviate from the designed behavior because it's mathematically proven to follow that behavior. Okay? So this project is called SEL4. It was developed by a group who used to work at CSIRO at Data 61 called the Trustworthy Systems Group. So I'm not quite sure why, but in 2021, CSIRO decided that they were no longer going to host the Trustworthy Systems Group. But fortunately, they live on New South Wales, and here are some of the members. So some of my former PhD students have worked with them and had a really good time. But I'm going to concentrate on the theory. Okay? So the theory is the following. Okay, so I've listed here a couple of things, which I'm not really going to talk about. So this is type theory. So this is the BDI of Per Martin Löf, who is a Swedish philosopher and logician and mathematician. And so he's responsible for something called type theory, which is basically a mathematical framework for studying programming languages and also for in the same language for kind of proving things about them. So it's sort of fascinating sort of mix-up of the computing and the logic you need to sort of verify that the computing does what it's supposed to do. And so that's so that's the kind of framework in which this project was done. So getting a little bit further towards kind of pure mathematics, there's something called domain theory, okay? So this is Dana Scott, who originated domain theory. So he was a professor at Carnegie Mellon University in the States. And so domain theory a domain is like a mathematical model that represents a kind of domain of computation, you might think, and sort of the world in which computations can happen. So I'm going to be a bit vague about what exactly that's supposed to mean, but it's a sort of major way in which we can represent computation mathematically. And then the final one is the one I'm going to talk about today, which is games. Okay? So you've probably all heard of John Nash and his kind of economic games and the prisoner's dilemma and things like this, okay? So these are quite a different kind of game. So those ones are kind of very raw and bloody and kind of, they're all about who wins and who loses and how much do they win and how much do they lose. So the games we're going to consider are a bit more like sports day in that it's not necessarily the winning or losing that's important, it's the taking part. And you'll see what I mean in a minute. Okay, so I'm going to start with a very boring game. In fact, the world's most boring game. So you've all played noughts and crosses, or tic-tac-toe, or whatever you want to call it. So this game is going to be tic-tac-toe, but on a 2x2 board. Now, to make it slightly less boring than it might be, I'm actually going to make it so that you can't win by making a diagonal line, because if you do that, then it would just be incredibly boring. Okay, and so what we're going to do is we're going to take turns in playing this. Okay, so maybe, does someone want to play this game with me? Anyone? Top left? Over here, someone? Yeah, okay. All right, do you want to go first? Why don't you go first? Top right. Okay, top right, there we go. Okay, so you're going to go top right. So then I'm going to go here. Where would you like to go now? Bottom left? Okay, and then I'm going to go bottom right. And there you go. So we've managed to force a draw in this game. Now, of course, if you had said bottom right instead of bottom left, then you'd have won. But you're being very polite and thought it was probably a bad idea to beat the speaker. However, in fact, the person who goes first can always win this game. And so that's a feature of the games we're going to have, that the first player can always win. And in fact, we can write out all the possible ways that the first player can win. And so here we are. Okay, so you probably can't see this, but fortunately I can do this. So this is the game tree. So we start here. And so what happens is, first of all, the opponent, as his opening move, just draws the board down. And so then this person, who I'm going to call player, who plays in purple, gets to play a circle as their first move, and they can do that in 4 possible ways. And then I, as the opponent, can respond in those 3 ways, like that, and then so on. And you can see here, in these ones, the first player will win the game, and in these ones, it'll be a draw. Okay? And so most of the time, the first player can win, but sometimes there can be a draw. Now, what we're interested in are ways in which the first player can force a win, and we're going to call that a winning strategy. And so basically, we can illustrate that just by sort of highlighting a bit inside this tree. Okay, so here is a strategy for the player who's playing O. Okay? So it says we start down here, and then I'm going to start by playing top right. And then if my opponent plays top left, I'm going to play bottom right. So that's what you decided not to do. You said, let's play up here. And then we got to here. But if you had been a bit more John Nash about it, you'd have played that, and then you'd have won. Okay, and then, but if instead I played down here, maybe we choose to do this, and so on. Okay, and the point is that we choose a thing such that no matter what move the opponent makes, we respond in a way such that we're going to win. Okay, so that's a real-world game, but we can turn that into a sort of more mathematical thing just by forgetting what game it is we're playing, and we just keep this picture. Okay? Right? It's just like, here's the first move, these are the possible responses, these are possible responses to that, and you say, okay, well, how do I know when I've won? Well, the player who plays last always wins. That's the new rule. Okay? So here, purple wins because there's no responses by the orange player. Okay? So there we go. There's our first mathematical game. Okay. So this actually leads into the first thing in my title, which is computer games. Okay? Because we can do this not for this game of tic-tac-toe, but we can do it for more complicated games. So if you do it for 3x3 tic-tac-toe, there's 256,000 of these nodes instead of about 50. If we do it for chess, then it's astronomically large, like the number of entries is bigger than the number of atoms in the universe. And in fact, the number of entries, if I just take the first 3 levels, the moves in the first three moves in a game of chess, there's over 140 million entries there. So it's a much more complicated game, and we don't, as yet, know a winning strategy for it. And so we have to approximate. Okay, so we say, well, we don't understand the whole tree, but we kind of say, well, what's my best strategy, given that I can only see maybe 5 moves ahead, like this. And I'm going to estimate for each of the moves 5 layers ahead how good they are. Okay? And so this was actually first described by Claude Shannon in 1950, the idea of a computer playing chess. It then took about another 45 years or something like that before computers actually got really good at chess and could beat humans, and now they routinely do it, and even more recently they've become so good that they can beat computers at Go as well, which is a much more complicated game. However, that's not what I want to talk about. I want to talk about using these games to actually represent computing. So I've got 5 minutes left, and I'm going to be able to tell you just a few more slides about how we can use these games to actually do computing, to represent computer programs. So here are 2 really boring games. Okay? So in this game, the orange player starts by asking true or false, and then the blue player responds by either saying true or false, and then they've won the game. So this is a really bad game. That's why I say it's not the winning or the losing, it's the taking part that counts. Because the player who plays blue has 2 strategies for this game, right? They can either say true, I win, or they can say false, I win. But those 2 strategies give you information. It's like they're saying either true or false, okay? So the strategies for this game encode the 2 Boolean truth values, true and false. Similarly, for this game here, the strategies that the player has, the blue player has, is, so the orange player says, think of a number, and then the blue player just responds by saying a number between 1 and 10, okay? They're always going to win, but each of those winning strategies encodes a different number, which is their response. Okay, so we're just going to try something a little bit more complicated than that. So I'm going to show you a construction. It's going to take some of these game trees, two of these game trees, and you turn them into a new game tree. So here's a game tree, and here's another game tree, which I've helpfully shown in pink and blue. And what we're going to do is we're going to stick them together. So we're going to take the blue one here, and then we're going to stick the pink one like this. But you see, I've taken the root of the pink one, and I've sort of stuck it onto the root of the blue one. And you'll see what happens is all the colours here reverse. So the roles of the player are interchanged in this game here. So that might seem like a weird thing to do, and you might wonder why on earth we're doing this. And I'm going to show you. So we're going to use the two games we had here, and we're going to apply this construction to them. And we're going to construct a new game, which is called Do You Like My Number? Okay, so you shouldn't confuse this game with Do You Want My Number? That's a different game. So the game Do You Like My Number? So the orange player says, do you like my number? And then the blue player has three choices. They can either say, yes, I do, no, I don't, or they can say, what is your number? So then, if they say, what is your number, then the orange player tells them what their number is. And you might think at that point, well, that's a very boring end to the game, because now the orange player seems to have won, and we don't have an answer to the question of whether the number was liked. However, we can actually do this, because there's a new rule here, which is that we're actually allowed to jump back to earlier parts of the game. Okay? So once we've answered this question, we can then jump back to here and answer the original question, which is, do you like my number? Okay? So a typical strategy for this game might be, as the blue player, the orange player says, do you like my number? I say, what's your number? And then maybe if the orange player tells me an even number, I say, yes, I like your number. So if I get 2, 4, 6, 8, or 10, I'm going to reply with true. And if I get 1, 3, 5, 7, or 9, I'm going to reply with false. Okay? So you can see that one of the blue player's strategies for this game encodes the idea of checking if a number is even or odd. Okay? And I can think of a different strategy that checks if a number is below or above 5. Okay? And I can think of an even other strategy that just allows me to pick out one of those numbers. Okay? Which is, maybe I decide I only like the number 3 and I hate all the other numbers. So I'm just going to say yes if you respond 3 and no otherwise. Okay. All right. So if you'll allow me just 2 more minutes, I'll show you the final slide because I think it's fun. It's all right. You can stop me. It's not that fun. So this is a game called Guess the Number. And so what do? We take this game, Do You Like My Number? And we take the game, Think of a Number, and we stick them together. And so what we get is a game where the player says, can you guess my number? And then this player says, well, hang on, what's going on here? Sorry, I've just had a sudden moment of unclarity. Okay, so this game is called Guess the Number. So this player says, what's my number? And then the other player says, well, do you like my number? And then he says, well, what is that number? And now my moment of unclarity, unfortunately, seems to have become all pervasive, which is very sad because this is a really exciting example to end the talk with. But I think I'm simply going to have to declare that I've managed to actually confuse myself, which is a shame. But in 10 minutes, I'll be able to tell you how to play the game of Guess My Number using this game tree. And I think I'll stop there on that real damp squib. Thank you.